Imagine trying to solve a puzzle with trillions of possible combinations. Even the world's fastest supercomputers can spend years searching for the right answer because they have to check possibilities one after another. Now imagine a machine that can explore countless possibilities at the same time, dramatically reducing problems that would otherwise take longer than the age of the universe to solve. It sounds like science fiction, but this is the promise behind quantum computing. For years, quantum computers have been surrounded by hype. Some people believe they'll replace every laptop and smartphone. Others think they're too experimental to ever become useful. The truth lies somewhere in between. Quantum computers aren't designed to replace the devices we use every day. Instead, they're being built to solve very specific problems that are nearly impossible for classical computers, no matter how powerful those computers become. To understand why quantum computing is such a breakthrough, we first need to understand how today's computers actually work. Every computer, from your smartphone to the largest data center, processes information using bits. A bit is the smallest unit of information and can only exist in one of two states, a 0 or a 1. Everything you watch, write, stream, or calculate is ultimately broken down into billions of these tiny binary values. Modern processors are incredibly fast because they can manipulate billions of bits every second, but each bit is still limited to being either a 0 or a 1 at any given moment. Quantum computers introduce something completely different, the qubit. Like a regular bit, a qubit can represent 0 or 1. But thanks to the strange rules of quantum mechanics, it can also exist in a combination of both states simultaneously. This property is known as superposition, and it's one of the biggest reasons quantum computers attract so much attention. A useful analogy is a spinning coin. When a normal coin lands, it's either heads or tails. But while it's spinning in the air, it isn't fixed in one position. A qubit behaves somewhat similarly, although the underlying physics is far more complex. Instead of committing to a single value immediately, it can represent multiple possibilities until it's measured. This doesn't mean quantum computers magically know every answer. That's one of the biggest misconceptions surrounding the technology. Instead, superposition allows quantum algorithms to explore many possible solutions in ways that classical computers simply cannot. Then there's another strange phenomenon called entanglement. When two qubits become entangled, they form a relationship that links their states together, even if they're physically separated. Changing one immediately affects how the overall system behaves. Albert Einstein famously referred to this phenomenon as spooky action at a distance, because it seemed to defy everyday intuition. For quantum computers, entanglement is incredibly valuable. It allows qubits to work together as a connected system rather than as isolated pieces of information. As more stable qubits become entangled, the computer gains access to an exponentially larger computational space, making certain calculations dramatically more efficient. Of course, building such a machine is much easier in theory than in practice. Quantum information is extremely fragile. Tiny vibrations, changes in temperature, electromagnetic interference, or even stray particles from the surrounding environment can disturb qubits and introduce errors. This process, known as decoherence, is one of the biggest obstacles preventing large-scale quantum computers from becoming mainstream. That's why many quantum processors operate inside massive refrigeration systems that cool them to temperatures colder than outer space, just fractions of a degree above absolute zero. These extreme conditions help protect qubits from environmental noise long enough to perform calculations. Even then, today's quantum computers remain highly experimental. Most contain only a limited number of reliable qubits, and researchers must constantly correct errors that occur during computation. In many cases, more hardware is dedicated to error correction than to solving the actual problem. Despite these challenges, progress has accelerated rapidly over the past decade. Companies like IBM, Google, Microsoft, and several startups are investing billions of dollars into quantum research. Governments are doing the same, recognizing that whoever leads quantum computing could gain enormous advantages in science. Another major application is optimization. Airlines scheduling thousands of flights, logistics companies planning delivery routes, manufacturers managing global supply chains, and financial firms balancing massive investment portfolios all face optimization problems involving countless possible combinations. Quantum algorithms have the potential to identify better solutions much faster than conventional methods. Cybersecurity is another field being transformed. Many of today's encryption systems rely on mathematical problems that are practically impossible for classical computers to solve quickly. However, sufficiently powerful quantum computers could solve some of these problems far more efficiently using specialized algorithms, potentially making current encryption standards vulnerable. This possibility has already sparked a global race toward post-quantum cryptography, new encryption methods specifically designed to remain secure even in a future where quantum computers become practical. Beyond business and cybersecurity, quantum computing could also revolutionize climate research, materials science, artificial intelligence, and energy development. Researchers are exploring new battery materials, cleaner industrial processes, more efficient solar technologies, and improved climate models that require enormous computational power. Many of these simulations push classical computers to their limits, making quantum systems an attractive alternative as the technology matures. Even with all this potential, it's important to separate reality from hype. Quantum computers won't replace your laptop, gaming PC, or smartphone. For everyday tasks like browsing the web, editing documents, or watching videos, classical computers are far more practical, affordable, and efficient. Quantum machines are designed for highly specialized problems where the laws of quantum physics provide a unique advantage. Another common misconception is that quantum computers are already outperforming traditional computers in every field. They're not. Today's quantum systems are still in what researchers call the noisy intermediate-scale quantum or NISQ era. They can demonstrate impressive capabilities in controlled experiments, but they're limited by hardware constraints, short coherence times, and error rates that researchers are still working to reduce. That said, progress is happening faster than many expected. Every year brings improvements in qubit stability, error correction, and processor design. Researchers are experimenting with different technologies, including superconducting circuits, trapped ions, and photonic quantum computers, each with its own strengths and challenges. It's still unclear which approach will ultimately dominate, but the competition is accelerating innovation across the industry. The impact of quantum computing may arrive gradually rather than overnight. Businesses will likely be the first to benefit, using quantum systems through cloud platforms to solve highly complex scientific and industrial problems. Most people may never own a quantum computer, just as few people own massive data centers today. Instead, they'll access quantum-powered services behind the scenes without even realizing it. History has shown that revolutionary technologies often begin in laboratories before quietly transforming everyday life. The internet, GPS, and artificial intelligence all followed that path. Quantum computing appears to be on a similar journey, moving from scientific curiosity toward practical applications that could reshape entire industries. The biggest breakthrough isn't that quantum computers are faster at everything. It's that they approach certain problems in a fundamentally different way, opening possibilities that were previously out of reach. While there's still a long road ahead, one thing is becoming increasingly clear. Quantum computing isn't just another upgrade in processing power. It's an entirely new way of thinking about computation itself. As the technology matures, it could help unlock discoveries in medicine, cybersecurity, materials science, and countless other fields that today's computers simply can't tackle alone. The quantum revolution may not happen overnight, but when it arrives, it has the potential to redefine what's computationally possible for decades to come.